So in Proposition 4, we got our first conic section, that of the circle. And we found that we can get a circle if our cutting plane is parallel to the circular base, right? So in this case, if we have our axial triangle, A, B, and C BC being the base circle, if our cutting plane is parallel to it, we would get this red circle, DE. But now the question is there any other way we could cut the cone or the conic surface and get a circle? Obviously we could just move the cutting plane up or down, but in terms of angles, if it's parallel to the base, yeah, we get a circle. But is there a different angle that we could use to get a circle? If we're dealing with a right cone, then no, unfortunately. But if we're dealing with an oblique cone, there is a way that we can do it. And this is when he uses this term subcontrary-wise. Basically, all he means by that is a cutting plane at a certain angle that kind of already exists in the oblique cone. So that's what we have here. We have an oblique cone, A, B, and C, and BC is the diameter, so triangle A, B, and C is our axial triangle. We keep this red circle that's parallel to the base. We know that is going to be a circle for sure. But what he's going to do then is the purple circle, we want to prove it's a circle, that purple curve is at a cutting angle that he calls subcontrary-wise. And what he means is that the angle between the plane and the line AC is the same angle as the base circle in the line AB. And that's what I have over here in figure 1. So if we kind of just ignore everything else and just kind of extract this picture of the axial triangle and then everything else that kind of comes with it, DE is the diameter of the red circle, and GK is what will be the diameter of the purple circle, and then BC, etc. All right, so the cutting plane that generates the purple circle is at such an angle such that AKG is equal to ABC. These two angles are equal. And while we're at this figure, let's just go ahead and fill out a few other things that we're going to know about it. Since the red circle, that cutting plane is parallel to the base, that means angle ADE is equal to ABC, right? If we remember the properties of parallel lines cut by a transversal, we know that this line is parallel to this line. Therefore, these are corresponding angles and are therefore equal. We also know that the three angles of any triangle always add up to 180 degrees, or two right angles, which means that, we can go that way or a different way. Since angle A is common for all three triangles that we're going to be looking at, we can then further deduce that angle BCA must be equal to angle DEA, right? Because that would be the third angles for the triangle ABC and ADE, right? So we know those two angles have to be equal, but then also the third angle of triangle AGK must also be equal to those two. All right, so from here, what we're going to end up looking at is this kind of section right here. Because we have all these equal angles, and again, you can go through his demonstration, we can prove that triangle 1 and triangle 2, that is, what's this point called? This is F, right? DFG and KFE are going to be two similar triangles, therefore their parts are going to be proportional. And the reason that becomes important is because of a little piece of geometry that he reminds us of. If we have a circle like DE, and a diameter DE, if we drop some line from the circumference perpendicular to the diameter, like HF, which is how HF and LM were produced, and those are parallel, then that perpendicular line is going to be the mean between these two parts, FE and DF. It's going to be the geometric mean. Another way to think about it, if we want to do a numerical example, if FE was 8 and DF was 2, and we had a diameter of 10, if this were the case, HF would have to be 4, the geometric mean between 8 and 2. Another way to think about it is, and again, the way this is proved is through a lot of similarity of triangles, but we would essentially show that 2 is to 4 in the same ratio as 4 is to 8. Another way to think about it is if you take the square of HF, it's going to, if you remember from proportions, the product of the means is going to be equal to the product of the extremes. So 4 times 4 is going to be equal to 2 times 8, or the rectangle of DF EF. So in this working of the circle, if we have this diameter and a perpendicular dropped, the square on this perpendicular is going to be equal exactly to the rectangle formed by the two parts of the diameter. And that's true for any perpendicular that you can drop. And because this is true, we can say about our red circle that HF squared, literally a square composed of HF, is equal to the rectangle of DF EF. But because of all the jazz that we did up here, improving these different parts are, not just similar, but are actually congruent, then GF is going to be equal to, I want to make sure I get this right. Yeah. GF is going to be equal to EF, and DF is going to be equal to KF. Therefore, a rectangle of DF and EF would be equal to a rectangle made up of the parts KF and GF. So this is kind of step one. Step two, this square on HF is equal to the rectangle made up of these two parts. But because of all the similarity and congruence of triangles, DF and KF are equal, EF and GF are equal. Therefore, a rectangle made up of DF and EF is going to be equal to a rectangle made up of KF and GF. Therefore, the square on HF is going to be equal to the rectangle made up of KF and GF. Right. And we're done. Because this is only true if the purple curve is a circle, GK is the diameter, and HF is perpendicular to the base. All of that, which we already established, I didn't bother going through the steps, but you can read it in Apollonius himself. But this truth is only applicable if GK is a circle. And since it is true, GK must be a circle. Therefore, when we have an oblique cone, we have exactly two ways to cut the cone and generate a circle. Parallel to the base and subcontrary-wise to the base. That is at the same angle as the obliqueness. You can think of it that way. Now, the reason why the right cone is kind of boring is because both of these cuts are the same cut. If we look back at our picture of the right cone, this angle, ABC, is already equal to this angle, AED, right? Right, since this is a right cone, these are actually all going to be equal, right? These are two isosceles triangles. So the cutting plane that gets us DE is both parallel to the base and subcontrary-wise to the base. Namely, it's at the same angle. And that's it. Excuse me. We just explored and proved one additional way to generate a circle from cutting a cone. And there are two ways we can cut an oblique cone to get a circle. Now, our natural question should be, what if we tilt our cutting plane more? What if, after this angle, we tilt it a little bit more? What if we make it vertical? What kind of section will we have then? Well, that's what it's going to get to in the ladder props. All right, that's it.